So good morning, everyone. Great to see you here. And you already mentioned my name and that I'm here today to introduce you to Quest. So the thing is that nowadays headlines about misbehaving, let's call them AIs, have kind of become the norm. We have heard about groups of people being misdiagnosed, being judged unfairly in court, being disadvantaged in hiring, and so many more things that I'm going to spare you. And that doesn't exactly build trust in the concept of AI systems. In fact, to be honest, I am much more surprised if on any given day, I do not read on Twitter about anything like a scandal or something misbehaving, or at least being peculiar. So how exactly does that keep happening to us? And for the purpose of this talk, I'm going to boil this down to two major reasons. Right. And the first of them is we don't really understand these systems. So don't worry, the slide is actually meant to show you that you can't understand it at a glance. This is the architecture of AlphaGo Zero, and I'm sure some of you have heard of that. And this is just after someone has tried to make it intuitive and has tried to create an overview. And this is just the architecture. We're not talking about model parameters or anything here. I don't have a hope of understanding any one of those. And even if I could understand one, I wouldn't have a hope of capturing 10, let alone billions. We have increasingly bigger and more complex designs. We have opaqueness by design. We have closed source tools, all these kind of things in a lot of state-of-the-art solutions. And that makes it so that we can't really tell you how it works inside. But apart from that, we have AI-based systems basically everywhere. Pretty much no aspect of our lives has not been influenced by a learned system. I've just listed a few here that are especially relevant for explainable AI. So the obviously critical ones, but also those concerned with who gets what kind of information, think fake news, but also consumer recommendations. And what they have in common is that they all build on trust. We need trust by the user to work with them appropriately, or on the other hand, we need mistrust to decide not to use them. So let's look at an example. We have a printing company here that monitors the state of their machines with this database. We have the days since the machines have last been serviced, so the times they've been running since an engineer had a look at them. We have downtime within that time frame in hours. We have a couple of other parameters. Is the machine currently running? What type of machine is it? And we need to make a decision on whether this machine should be serviced today, whether an engineer should go there and check it through. And we have to find a compromise, because if we do that too often, it gets expensive. We need a lot of engineers and we have a lot of downtime. We need to shut the machines down. But if we do it too little, and we could have faults, we could have something breaking. We already have a model now that is producing this kind of output on whether any one machine should be serviced today. This is working fairly well. We don't have a lot of faults. It's not too expensive. But people don't trust the system. Why don't they? Because they can't make informed decision on what to actually do in their job. They just get this kind of yes, no, and they can't decide if maybe they don't have enough engineers that day, what machine to choose, or maybe if the system is doing something wrong, they can't judge that. So we need more information. For this purpose, we're going to look at machine number 5. And we're going to have a look at the engineer that has been given this machine to service today. Sorry, I think my hair is messing with the microphone. And we could also look at the same data in this kind of projection view, right? So we're just looking at the last service time and the downtime. And we have our model that makes kind of an output for yes or no. We're now interested in the gray dot, which is machine number 5. And we want to find an explanation of why the machine has chosen this machine to be serviced today. The model has chosen this. And this explanation should help the engineer build some kind of mental representation on what this model does. Because if they have a mental representation, they can reason with it, which is what we normally do every day. But the entire model is complex, much more complex than, of course, this little kind of view that we have here. And right now, we're only interested in machine 5. Which basically means we now have a local and a post hoc explanation problem. One established way of dealing with this is called LIME, and this is what LIME would produce. It would produce a linear model that approximates the original opaque model within a local neighborhood that kind of fades out towards the edges. It's always circular, and the output it gives you is feature importance. Another one would be anchors. Anchors creates if-then rules, and they always take the shape of kind of these rectangular neighborhoods that we judge in, which are aligned with the axes, and everything within that would have the same output. What we suggest is this. This is our approach, and we kind of build a local neighborhood as well, but we make it cover both sides of the decision surface. But how do we get from just the dots and just the dot models to this kind of output? And what would it look like to the engineer? Because we can't always assume we have 2 dimensions, right? We suggest it could look like this. Because people working with data usually have an intuitive understanding of predicates, of queries, and they can work with this. Because basically what this is telling us is that if we have a certain relation between the downtime and the time since the machine has last been serviced, meaning was the machine running a lot or not, that in this local area can tell us whether it makes sense to service the machine. So let's start from the top. We have our decision surface, we have our data sample, and what we do next is we choose a feature subset. We can do that because we're only looking at the local neighborhood, and within that local neighborhood, the model is much less complex than in a global view. So we can select just a subset of the features to simplify the problem. What we have next is a certain set of templates. We call them explainer classes that basically have a shape of neighborhood and a decision surface within that. And when we have those, we can fit them to the problem at hand. We can make them as close to the local neighborhood that we want, make them as big as possible, make them as accurate as possible. And once we've done that, we can select our winning candidate. And since we know our templates, we can now generate the query pair, one for why does the model recommend servicing, and one for why does it not recommend servicing for this local neighborhood. It's as simple as that. In other terms, so if we want to take a framework look at this, we start with the model, we start with the data set, a sample, and a budget for complexity. And you can think of the budget as just the number of predicates that we allow in the resulting query. And then we have the initialization phase, which is where we do this feature subset selection. We have instantiation, where we take basically any explainer class and apply it to the problem at hand. We then have the training phase, where we create a lot of instances for each of these classes and fit them to the problem. And while we do that, we can always eliminate the ones not applicable or the ones that are not working for us, right? So we have a pruning process where we can also use something like successive halving. And finally, we select the winning explanation from our candidate pool. And we're done. Just to give you one more intuition, how this could look different from before, this is another explanation, another model, which already takes a form that, for example, we can't really approximate with anything that we've seen previously. Anchors can only ever cover one side of the decision surface and also only one form. But we can cover different types of forms because we have the different templates. And this, for example, could be based on a surrogate model of a decision tree for our local neighborhood. And with that, I hope that I have sparked your curiosity in query-driven explanations, and of course, our framework to create them. Thank you very much.
Could you talk more about the templates a little bit? Like what kinds of templates there are?
Yeah, sure. Okay, so the question was whether I can, no worries. I was in the process of doing that. So the question was whether I can talk a little bit more about the templates and what kind of different templates are. And I'm just going to start with this one because it's the simplest one. And it's basically a rectangular neighborhood that you would constrain by doing like the value on the x-axis has to be lower than this, bigger than this. And on the y-axis the same. And then within that, you would train a linear model, basically an explainable linear model that would give you the distinction between the two sides, right? The angle could vary on that, but you would also always have that rectangular thing and the linear model, which basically means a line through that. And then on the other hand, we have the decision tree. Okay, I'm going to just skip through that, which basically means we can have kind of these non-comprehensive forms, right? So if we have a decision tree, we could have one area that's in the light blue down to the right and down to the left, and they might not necessarily make a rectangle together, but anything we can kind of put in a decision tree on these dimensions, we could put into shape here. So we would have not a line as a decision surface, but something more complex. But we could also have, which is the template from before, distance-based thing, which would be the round template, right? We choose any point in our feature space and we go, like, if it's a very short distance from that, it's the one output, and if it's further distance from that, it might be the other output. So those are the basic three that we first suggested. But you can basically anything that you can formulate on how to put it in a query, you can use, which makes this quite extensible.
a lot of time the features that we get are not human comprehensible, right?
Yeah.
Is there a translation step? Or how do I say this? How are the templates ever useful if the features themselves are in some strange space that we can't understand?
Yeah, so not really.
Okay.
So we're basically building on either having human understandable features or having a human make a translation, because we can only work with what we have, right? If we don't have domain knowledge and we don't have human understandable features, we can't really make that translation automatically. But what we can do is use user-defined functions. So instead of having a column in your database that you can't really interpret, what you could do is have several that are interpretable, but more basic, and then give the machine a user-defined function that combines them in some kind of more complex way, that we could use to simplify the feature space, but still kind of keep the original interpretable attributes.
Great. Thank you again. Oh, do you have a question?
No.
What's the use case for a lot of these templates? Like, for example, take decision tree template. If a decision tree accurately summarizes the results of the model, why don't we just create a decision tree to begin with? Why do we have this more complex model we're trying to simplify? Does it only summarize like part of the model? I'm just trying to understand exactly how it works.
Okay, so if I understand your question correctly, the question is, on the one hand, why do we have the several templates? But maybe on the other hand, why do we use surrogate models in the first place instead of just using the surrogate models
No.
as the model?
More the second part, yes.
Okay, the second one. So the thing is that we only use the surrogate model in the neighborhood, right? We're only using it around the local point, and the complex model is always globally. So what we're assuming in this example, but we might have other situations, that the black box model already exists, the opaque model already exists, and it's working well, and we don't want to replace it. And the only reason why we can approximate it properly, appropriately, is because we reduce the complexity by reducing the neighborhood size.
Okay, thank you.
Yeah.
Thank you again.